Hello everyone. Well, it is a pleasure for me to introduce today our speaker, José Carlos Abadillo-Uriel. He's currently at CEA Grenoble. He did his PhD here in the institute, where he studied silicon-based quantum computing, basically or focusing in the role of holes in silicon and germanium. And then after finishing his PhD, he went to, he spent 2.5 years in the University of Wisconsin-Madison, and he's already been 2 years in Grenoble. So today he's gonna tell us about the manipulation and extending the coherence of Hole spin. So welcome and thank you.
Thank you for the introduction, and well, it's a pleasure to be back here, and many known faces, some other faces that I don't recognize, but I guess life goes on. So yeah, today I will be talking about manipulating and extending the coherence of whole spin qubits. So let's go with it. Is it working?
No.
Okay, there we go. So yeah, this is the outline of the talk. I will start with a brief introduction into my field of semiconductor qubits. And then I will be going through a series of works that we have done along these years. I will present how to manipulate whole spin qubits, how you can still have a good coherence in these types of qubits, and I will also present our recent result on spin-photon coupling, which is an experiment theory collaboration. I will finish with some conclusions on this whole spin qubits. So, well, many groups around the world are trying to build this quantum computer, and well, what's the point in the end? I don't think I need to tell you this, but in the end we want to do this for efficiency, right? We want to find this kind of platform in which you can find algorithms where you can improve information security, database search, and maybe the most interesting part for us as physicists is that we can, in principle, in this kind of platform, perform quantum simulations of complicated molecules or new materials. And but maybe just again, because we are physicists, we also do it because it's fun and it's interesting for us. So there are many platforms for this kind of qubits, and well, nowadays the leading technology is transmons, which is based on a semiconductor platform, superconducting platform, sorry. And well, these transmons are the ones that are used with IBM, Google, and well, there are, I think the most recent result they had like 433 qubits. On my side, I work mostly with semiconductor qubits in quantum dots, like silicon quantum dots, gallium arsenide quantum dots, and germanium dots. And I want to show you today that this platform is also very interesting for quantum computation. And in particular, I wanted to motivate this platform. First of all, what we all say in these slides is, you know, semiconductors are already in the industry of classical computation. So in principle, you should be able to adapt the technology to create a future quantum computer based on this very same technology. And well, there are some recent results that show that this kind of technology can exhibit good coherence properties in the spins of electrons, and you can also show that you can manipulate using electric fields these qubits. There's also the idea that this kind of semiconductor qubits can be scaled very well. So this can be observed already with this diagram. You can see that transmons are already pretty big. The unit cell, let's say, of transmons is very big. So if you want to make a realistic quantum computer of, let's say, for realistic applications, I mean, of 1 million qubits, Well, these transmons are going to have to be, well, the quantum computer is going to be very, very large. So in that sense, semiconductor qubits are very promising because, you know, the unit cell is in the tens of nanometers. So in principle, if you have to pile up thousands, millions of qubits, it should be much easier. Or, well, in the end, we don't know how it will look like in the future, but maybe we will have hybrid technologies in which, for instance, you take advantage of the transmons. You have, let's say, a core with transmons, and you have also semiconductor dots, which are maybe the biggest part of the quantum computer. We don't really know yet. But it's a possible scenario. And another interesting point is that there are already demonstrations of high temperature operation. And with high temperature, I mean in the few Kelvin regime. Semiconductor quantum dots can work at these temperatures, while superconducting qubits like transmons, they need to operate in the tens of millikelvin. So how do you operate these quantum dot qubits? I wanted to illustrate this with a very simple example, which is based on the original idea from Loss and DiVincenzo of spin qubits. So I have here an example with a heterostructure with silicon and silicon germanium. And well, basically you have a part that is made of silicon, and you have a few gates on top in which you can use to define an electrostatic potential in which you can trap electrons or holes. And in these electrons, you have the spin degree of freedom, which is a natural two-level system, and you can define your qubit. The idea is that you can, for instance, if you have in holes a spin orbit coupling mechanism, you can use these gates, these very same gates, to perform manipulations of the spin. Or in case you have electrons and no spin orbit coupling, you could use magnetic fields, oscillating magnetic fields. For two-qubit gates, you could, for instance, use a tunnel gate to change the tunnel barrier between two distant electrons, and to use the exchange interaction, which has already been made in the literature. For readout, there are many mechanisms. Maybe the most typical one is spin-to-charge conversion. And just for a bit of history, well, the original implementations were actually not in silicon and silicon germanium. They were in heterostructures made of gallium arsenide, because they were easier to implement experimentally. But in the end, these both gallium and arsenide have non-zero nuclear spins. Well, the stable isotopes of gallium and arsenide, the nuclear spin are non-zero. So you basically, if you define a spin qubit in these devices, you have a nuclear bath that is affecting the coherence of your spin. In the case of silicon and germanium, the most stable isotopes have nuclear spin 0. So there is there's no nuclear bath, and you can actually do isotopic purification to remove any isotopes that have non-zero nuclear spin. So you can improve quite a lot the coherence of these qubits in both silicon and germanium. So, well, just a simple slide on the status, just to give you an idea of how the field is going on. So right now, there are very, very good single qubit gates in both silicon and germanium with fidelities above 99.9%, and there are many groups that have achieved this number. And there are already a few examples of very good two-qubit gates are above 99% of fidelities. The best processor is made in Delft with electrons, and there is a 6-qubit processor, which is illustrated here. And there have been demonstrations of these qubits at 4 Kelvin. Today, I will focus in particular on whole spin qubits. And these whole spin qubits are a bit peculiar compared to electrons, because electrons in silicon and germanium, they have a very low spin-orbit interaction, which is in principle very good in terms of coherence. So, you know, your spin is not coupled to the electric field. And in this way, your coherence times are going to be good. but at the same time this makes the manipulation of the spin very complicated. So the idea is that you can solve this issue just by defining your qubit in the spin degree of freedom of holes. Now, holes in silicon and germanium, they inherit the behavior of the top of the valence band at low temperatures. So this means that they have an intrinsic spin-orbit interaction. And in this way, you basically couple the spin degree of freedom of this hole to its motion. So if you can shake the whole wave function with electric fields, you can manipulate the spin electrically. At the same time, holes are very interesting creatures, and there are many properties that you can tune electrically, like G factors. You have RASHBA spin orbit coupling. You can find sweet spots in which you are insensitive to charge noise. I will get into details of that. These hole spin qubits have been growing quite fast in the last few years. So in silicon, the first demonstration was made in 2016. And ever since, there have been nice improvements. There is also the first demonstration in germanium in 2020. And currently, there is a 4-qubit processor with single qubit gates above 99.9% and a 2-qubit gate with 99% in germanium. There are already good numbers in terms of coherence, which is a work I will address today. And there's also a demonstration of a hot qubit operation in the group of Basel. I go to the second part of the talk, and which is about how do we manipulate the spin of a hole in these devices. So as I said, you have this intrinsic spin-orbit interaction of the hole. So you couple the spin to its motion, and you can use gates to move the hole and perform operations. In that sense, there are a couple of mechanisms that are very well known. There is okay, now it works. You have the RASHBA spin-orbit coupling. I will get into details in the next slide. And you have also the G-tensor modulation resonance, which it's a different mechanism in which you basically deform your whole wave function to change the G factors, and in this way the whole, the spin sees an effective magnetic field as a function of time. So you basically have this kind of effective Hamiltonian in the Kramer's doublet of your whole. You have basically the ZEEMAN energy. You have this RASHBA type of interaction that you can use to perform operations, and you have also the variations of the G matrix of your whole. So a bit more details on RASHBA spin-orbit interaction. This arises from the lack of inversion symmetry. So in the end, and these devices, due to geometry reasons and also because you push the whole wave function against an interface, you reduce this symmetry, and you end up inducing this RASHBA interaction. So the idea here is that you can shake the hole. You can move it from one side to the other with some gates that are nearby. And in this way, if you have the modulation frequency is equal to the Larmor frequency of the spin, you can perform Rabi oscillations. Now, in planar isotropic dots, which are, for instance, those that are used in Delft, the thing is that these dots are very isotropic in plane, and in this case, you don't have a linear RASHBA, you have a cubic RASHBA, and which has this shape here. So you can see that there's a cubic part in momentum, which means that you couple your orbital degree of freedom to an excited state that is very far away in energy. So this mechanism is basically not very efficient for electrical manipulation. We have also one term here which allows manipulation through the lowest orbital excited state. But in this case, this guy is proportional to this gamma minus here, which is a parameter that depends on the effective masses of the hole. And in the case of germanium, gamma 3 and gamma 2 are very similar, because in germanium you have basically a very isotropic material. So this means that even this term is very, very inefficient for electrical manipulation of holes in germanium. It can be better for holes in silicon. And now the main ideas to improve and get better RASHBA interactions for manipulation is to, you go to nanowires in which you have a weaker confinement direction, and in this case you have linear RASHBA, which usually has this kind of shape in which you have the momentum along the weakest confinement direction. You shake the dot along this direction, it couples through the spin through this sigma y. In case, this sigma y appears only if your strongest confinement direction is along the z direction, which is usually the case in these nanowires. And this interaction is, the strength of this interaction is given by the so-called spin orbit length, which can be very, very small in silicon nanowires. And in the end, this spin orbit length, you can see it physically as the length over which you move your hole, and the spin is precessing around the y-axis under this Hamiltonian. So after this LSO, your spin is able to precess entirely. So in this way, this linear RASHBA allows to have a much more efficient manipulation. There are also ideas to implement this in germanium, for instance, with planar dots, in which you have made your gates anisotropic, such that you end up with anisotropic planar dots, and you can then have anisotropic dots. This appears in this paper here. The other mechanism that is well known is G-tensor modulation resonance. The idea here is that holes have G factors that are anisotropic as a function of the orientation of the magnetic field. So you have what is called a G matrix, and in principle, you could, this G matrix depends a lot on confinement details of your hole. Just to give you an idea, in the end, your ground state, your heavy hole ground state, is composed of both contributions from heavy holes and light holes. Now, heavy holes have a very large vertical G factor, but they have a very weak in-plane G factor. On the other side, light holes have large in-plane G factors and weak vertical G factors, which means that in the end, if you can change the mixing between heavy holes and light holes in your ground state, you can actually change the anisotropy of your G matrix. And this is something that you can do. This is something that you can do with gates by just pushing your whole wave function against an interface and changing the orbital shape. The idea here in the end is that you shake your dot with just a top gate, for instance. In this way, you deform the wave function, you change the mixing between heavy holes and light holes, and you induce an effective, from the point of view of the spin, an effective magnetic field that changes the spin. This dominates for small dots in the end, while RASHBA dominates for larger dots. But still, it seems that these two mechanisms that are very well known in the literature, they don't explain everything. For instance, you can go to the paper from Delft with a 4-qubit processor, and these guys put the magnetic field in plane along the x direction, along one of the main crystallographic axis of the germanium. And in this case, you expect cubic RASHBA to appear and dominate. GTMR with the in-plane magnetic field is very inefficient. And in principle, your effective Hamiltonian looks like something like this. So you have your Larmor pointing along the x direction. You have the spin orbit, which is also effectively a sigma x, and the modulations of the G factor also go with sigma x. There's no way you can have a Rabi, there's no transverse term compared to the Larmor vector, so there is basically no way of performing Rabi oscillations here. So there's something missing in the literature, and we were interested in this puzzle, and we wanted to understand what was going on. So we thought, well, if the basic theory doesn't explain all of this, let's go with realistic simulations and see if we can find out what's going on. And what we did here was to, we took a device that looks very much like the one in Delft, in which you have basically this central gate under which you define your hole, and you have these lateral gates or on top and bottom, which you can use to shake the hole and perform manipulations. So we made the simulations using a Poisson solver. We use the Kohn-Luttinger Hamiltonian for describing the hole, and from this we can extract, we can solve the Schrödinger equation and take the ground state, the heavy hole ground state, and extract the G matrix of this Cramer's doublet. And from this we can just try to get the Rabi frequencies and see what happens. And well, this is something that we have worked on, and it appeared on arXiv quite recently. So this numerical experiment that we performed is very consistent with the observations from Delft, in the sense that we find that indeed if you do this and you shake your hole with these lateral gates, you have here that there's a peak, there's a Rabi frequency peak for in-plane magnetic field. So you have here in this plot the Rabi frequency as a function of the orientation of the magnetic field, of the applied magnetic field. And if you, well, basically magnetic field along the x direction will be just here, and we observe that this is actually the optimal working point in terms of Rabi frequencies. This is the place in which you can manipulate most efficiently your hole. This is surprising, although the observations were consistent, because in the end what you expect in these planar dots is this shape here. So you know there is this background. As you get closer to the vertical, to the magnetic field pointing along the z direction, you have this background, which is summarized here, which is basically your cubic RASHBA. So cubic RASHBA appears only if your magnetic field is along the vertical direction. This was expected, but this peak was unexpected. An interesting peculiarity of this peak is that, you know, RASHBA appears due to the lack of inversion symmetry, right? So you need a vertical electric field to enhance RASHBA. But this peak in here, if you go to zero electric field and the hole is not against an interface, just in the middle, this guy is maximal, which was quite surprising. And so we wanted to understand this, and we turned on and off things in the simulations until we found the culprit, which was in the electrostatics of the device. In the end, and you will see this everywhere, we are theorists and we simplify things. So everybody does this harmonic confinement to define, to describe these quantum dots and a vertical electric field that pushes your hole against an interface and so on. But in reality, the electrostatics are a bit more complicated. You have here a plot of the potential as a function of the position, and in here you can see this small region that corresponds to the germanium quantum well. And in the end, since the gate is finite in size and it's at a finite distance, the potential is a bit more complicated than this. And in particular, the main ingredient, the basic ingredient for this is not the anharmonicity, which is could be a possibility, was the fact that in the end, this potential also depends on how far you are from the gate. So you can see this as the harmonic strength of your confining potential, depending, it changes as you get closer to the gate. Once you consider this non-separable potential, you can actually reproduce this in plane feature, and this is something that we checked with a theory. So So I don't have many slides with equations, but this is one. And you have here the convolutional Hamiltonian, which basically describes holes in these devices. I won't get into details, but basically gives you the kinetic part of the hole. There's also the ZEEMAN part, the ZEEMAN contribution. And if you add this in plane harmonic confinement, that includes this non-separable term. And well, we also include strain, because in these devices there is a lattice mismatch between silicon and germanium, so strain appears naturally. If you include all of this, you can do perturbation theory to your ground state and get an effective Hamiltonian that looks like this. So you basically have your ZEEMAN Hamiltonian plus this kind of term that depends on the in-plane, the electric field that you apply. And there are these coefficients, lambda, that couple your in-plane magnetic field through sigma z. So when the potential is separable, you can calculate that these lambdas are actually 0. Physically, you can see this as, in what people think happens when you shake the hole in plane is that you just move the wave function, but you don't deform the dot. But what happens is that since the gate is the potential is non-separable, when you shake the dot, when you displace it, in fact, since the harmonic confinement depends on the vertical position, how much it is displaced depends on since the dot is the hole is finite in size, how much it is displaced depends on z. So you move it and it dances like a pendulum. In this way, the wave function is deformed during the way. So in a sense, this non-separable mechanism can be classified as a non-conventional GTMR mechanism, which consists on deforming the wave function of the hole. So yeah, just the take-home message of this part of the talk. We showed that this non-separable mechanism that was not considered in the literature can explain the results from of planar dots in Delft, which cannot be explained with RASHBA spin-orbit interactions, or at least not cubic RASHBA spin-orbit interaction, or conventional GTMR. So now I go to the next part of the talk, which is about coherence of holes. So I was talking about spin-orbit coupling, and that's nice. That allows us to perform manipulations with electric fields, but at the same time, we are coupling our spin to the charge, any charges that may be around in these devices. So charge noise is ubiquitous in these nanostructures, either silicon, germanium, gallium arsenide, doesn't matter. So this means that holes are going to have a lot of sensitivity to charge noise, and the question is then, can we mitigate the effects of charge noise in these holes in the same way it is done to achieve numbers that are similar to those with electrons, which have a much lower spin-orbit interaction. So this is something that the experimentalists in Grenoble thought about, and they made an experiment in which they have a silicon nanowire, in which, I will get into details with this slide better. So you have this silicon nanowire in which you have 4 gates, and you use your gate 2 to define your quantum dot, just under it, in which you place a hole, and a single hole. And in this device you can read out the spin using Elserman readout, which is a very typical one, and you can try to measure, to make measurements of the coherence time of the hole. So on our side, we made the modeling of the experiment in the same way as we did for the germanium quantum dots. And in this case, it was a nanowire, but the idea is the same. We basically have a framework which allows us to do the simulation of the electric fields with a Poisson solver, Luttinger-Kohn Hamiltonian. We extract the G matrix of the ground state of the hole, and we try to compare with the experiment, is the idea. So the experimentalists went ahead and they started measuring first the response of the hole with a magnetic field. So they measured the G matrices basically, so the G factor anisotropies. So this is something that you can measure just because you can measure the Larmor frequency of your hole, and you know the magnetic field that you apply, so you can extract the G factor as a function of the orientation of the magnetic field. And what they find is that, as expected, as expected in the literature, you know, you have these G factors that are quite anisotropic. On our side, we made simulations considering this order and also the geometry that they consider, right? And we find that our model can capture very well the G factors that they observe in the experiment. So you know, you have the dots that are basically the experiment, and you have the line which are coming from simulations. And the only thing that we needed to include a bit ad hoc was that in principle, from theory, you expect these anisotropies to be perfectly aligned with the axis of the nanowire. So you know, you in principle expect that this G factor is maximum or minimum at 0 degrees or 90 degrees in either of these plots. But we observed some rotations. It took us some time, but in the end we found that in these devices there can be some residual strain, and this residual strain actually can explain very well the rotations of the G factors. Then going about the initial question of this work, the experimentalists went ahead and they checked how much does the Larmor frequency of the hole depend on the gate voltages they apply. So you have here the derivative of the Larmor frequency with respect to the gates of the nanowire. If you remember correctly, well, the hole was just under gate 2. So in this sense, you can see that the Larmor frequency can be very sensitive to the gate voltages in this gate compared to the gate voltages in G1, which is the neighboring gate. And well, we saw that we also had very good agreement with our model and the experiment for this gate. Not so good under G1, which we suspect is because in the end we don't really know how the residual strains look like, and this can change a lot as a function of the position of the hole. Now gate 2 is just on top, so it basically deforms your hole, but G1 displaces your hole in this in this strain field. So this thing we are not capturing right now in the models. Now the most interesting thing is that you know, you want to make your qubit insensitive to charge noise. So what you're looking for is how to minimize this in absolute value these derivatives. So we find that there are two sweet spots for making the hole totally insensitive, well, first order insensitive to charge noise coming from gate 2. Unfortunately, we didn't find any sweet spot for these magnetic field orientations under G1 for G1, but we found that there is an optimal working point very close to 90 degrees in which you can minimize noise coming from this gate. So the experimentalists then did spin echo measurements. So they basically do these spin echo measurements in which they perform these pulses in which they can cancel part of the noise. I won't get into details of that unless you have any questions later, but what they find, they are able to measure the coherence times of the holes as a function of the orientation of the magnetic field, and they find that you can tune it quite a lot, and there's an optimum around 99 degrees, which is, well, I will get back, is very close to this sweet spot here and this minimal, this optimal working point under G1. So it's very consistent with the charge noise being the main decoherence source in these holes. So as you get closer to this optimal working point, you can extend the coherence of the hole up to 90 microseconds, which is comparable to the results that are observed with electron spins that are manipulable with electric fields, which means that they have a micromagnet, and in this case you can compare, and the numbers are very similar. At the same time, you don't really need micromagnets in this case, so it's a winning situation. So as a take-home message of this part of the talk, coherence of holes can be comparable to electrons with micromagnets, as I just said, and well, a couple of details that I don't really have time to discuss. You can even extend further decoherence with more complicated pulses like CPMG and get coherence times up to 0.4 milliseconds, which are pretty nice. And we find that if you do, instead of canceling part of the noise with spin echo or CPMG, you do free induction decay, we find that there is a limitation due to hyperfine noise at 1 microsecond coherence times. And well, the last part of the talk, I wanted to talk about this spin-photon coupling experiment that we have quite recently. So the motivation is the following. In my field, there are many 2-qubit gates that are very good, they are very fast, but they are all based on exchange interaction. And the exchange interaction is very limited in range. In the end, all the experiments so far in silicon and germanium, they are only considering this exchange interaction. They are very good single 2-qubit gates with 99% fidelities, but if you want to have a good quantum computer, you need to be able, people from quantum error correction codes, they tell you all the time that you cannot really correct all the errors if you just have nearest neighbor interactions. You need to be able to couple distant qubits. And there are many ideas in this sense. There is the possibility of doing charge shuttling in quantum dot arrays, like for instance you have an electron in a quantum dot and you just apply a series of gate voltages and you can move your electron from one dot to another that is far away. There are surface acoustic waves, there are many things, but today I want to focus on the idea of using superconducting cavities as mediators of the interaction between distant spins. So in this sense, there are a few experiments with electrons, and well, the idea is the following. The photons are quantized electric fields, and in the end, they don't couple very well to the spin of the electron, but they couple very well to the charge of the electron. So the idea with electrons is that you put this micromagnet to create an artificial spin orbit coupling mechanism, and in this way you can couple the spin to the photon. This has been done in the literature many times, and in these experiments they successfully couple the spin degree of freedom of electrons in silicon to the photons in a superconducting cavity. Now, the couplings that have been measured so far are in the tens of megahertz in the best case, while the decoherence rates are in the few megahertz, which means basically that you have a strong coupling between the photon and the spin, but it's not so good for 2-qubit gates. If you want to calculate fidelities of a 2-qubit gate with these numbers, it's not going to look good, not at all. So we made the question, what if instead of using micromagnets, we take advantage of the intrinsic spin orbit coupling of holes? And well, we have this preprint quite recently on this experiment. So this is what the experimental team in Grenoble did. So they fabricated niobium nitride, a superconducting cavity, and which they characterize. They have a resonator frequency, so the photon frequency is 5.4 gigahertz, and they find that they have a cavity decay rate when they couple to the quantum dot system of around 10 megahertz, which is standard. It can be improved in the future in principle. And the experiment can be summarized in this slide. You have basically this nanowire here, very similar to the experiment I was mentioning before. And this nanowire, the experimentalists were able to define a double quantum dot, under which they put a hole, and they couple the superconducting cavity through gate 2. So you can see the photons from the cavity. You can see them as a quantized electric field that comes through the gate 2, affecting the properties of the hole. And well, in general, we will apply an in-plane magnetic field which is compatible with a superconducting cavity. So first of all, we start at zero magnetic field, and the idea is to characterize the charge-photon interaction. So you have your double quantum dot with the hole, and you have a charge qubit. So you have first the resonator line, which is at 5.4 gigahertz, and then you have your charge qubit. When you are at the farther tuned regime, like at this star and this triangle, you are basically in a very biased situation in which you are basically the single dot regime. In this case, you have a very weak dipole, electric dipole, so you don't really couple very well to the cavity. And at the same time, your charge frequency, the charge qubit frequency is very far away from the resonator frequency. So there is not really an interaction between the qubit and the photon. Now, if you go to symmetric bias regime in which you have a zero detuning, then you have a maximum dipolar coupling. So you can couple better to the hole, to the photon. And in this case, you also are closer in energy to the photon. So what the experimentalists observe, they do proton spectroscopy measurements. So they send a proton, they get a reflection signal, and they can extract, as you can see here, where the cavity line is in frequency. So at farther tuning, they see that it's a line that aligns very well with the 5.4 gigahertz. But as you get closer to zero detuning, there's this dispersive shift due to the interaction with the charge qubit. And in this case, you can characterize this dispersive shift, and the experimentalists were able to fit the charge-photon coupling, and they found that it's half a gigahertz, and the tunnel coupling was very high of 9.6 gigahertz. So even though the charge qubit is very far in energy, they were able to measure a dispersive shift because the charge-photon coupling was very, very large. So now we want to introduce a magnetic field, because in the end we want to couple the spin degree of freedom, which has a better coherence than the charge degree of freedom. And if you have no spin orbit coupling, your charge spin qubit would look something like this. So you have here the frequency of your spin qubit, and since there's no spin orbit coupling, you are not coupling your spin to the electric field, so you have a perfectly flat frequency. But once you have spin orbit coupling, you start mixing the spin degree of freedom with the charge degree of freedom, with the orbital motion of the hole. And in this case, you mix all the different energy states with one another. So in this case, the spin has a bit of orbital motion in it, the ground state, I mean, the Kramer's doublet that we consider as a qubit. And you can see that the spin frequency can change as a function of the tuning. In general, unless I say otherwise, I will focus on this working point here, in which there's a sweet spot. The qubit frequency becomes insensitive to fluctuations in the tuning, and the coherence of the hole is much better in this working point. So then the experimentalists turn on the magnetic field, and what you expect in principle can be summarized here. So you have your cavity, which is at 5.4 gigahertz. You have your spin, which and the frequency of your spin increases as you increase the magnetic field. There is a moment in magnetic field in which you will have a crossing between the photon and the spin. Now, if there is a strong interaction between if you have successfully coupled the photon with the spin, then you should be able to observe an anti-crossing. And the this anti-crossing is approximately 2 times the spin-photon coupling, and this is exactly what the experimentalists observed in these two-tone spectroscopy measurements. They observe this anti-crossing that proves that there is a strong photon coupling, strong spin-photon coupling, which in this case is the spin-photon coupling is around 100 megahertz, which is already better than what had been done with electrons so far. So one thing that we observe is, as I was telling you before, holes are interesting creatures. They have anisotropies as a function of electric fields, magnetic fields, and so on. So they moved the magnetic field orientation, and well, in the previous case was 45 degrees away in plane from the nanowire axis. They aligned it with the nanowire axis this time, and they found that you can actually increase the spin-photon coupling up to 300 megahertz in this direction, almost 300 megahertz in this direction. In general, the experimentalists observed quite a strong anisotropy in this spin-photon coupling. So actually, the best case we can measure is at 3 degrees, in which the spin-photon coupling is 330 megahertz, which is one order of magnitude better than what had been done with electrons. So I will explain a bit briefly this anisotropy in terms of RASHBA, spin-orbit interactions. So in the end, the effective interactions, the effective RASHBA interactions in this nanowire, you have, as I was telling you before, you have a weak confinement direction in the nanowire axis. So given, so your hole, when it moves from one dot to the other, it moves along x. So you can characterize the spin-orbit interaction by this kx times some vector that is coupled to this the Pauli matrices. In our case, the spin-orbit vector is given by geometry, and it's basically pointing along the y direction as expected for RASHBA. And well, you have also the spin-orbit length that I was mentioning before, which is the length over which you have a spin precession around this axis as you move, as your hole moves in the x direction. So let's say you put your magnetic field in a direction that your Larmor vector points in the x axis, so the nanowire axis. In this case, since the spin-orbit vector points in the y direction, as the hole moves from one dot to the other, the whole spin precesses as it moves from one dot to the other. In the end, we find that in our experiment, the spin-orbit length is very similar to the interdot distance. So we basically have a spin flip in this direction and at these 3 degrees. On the other hand, if you have a Larmor vector that is parallel to the spin-orbit vector, so along y, you basically have that your spin cannot precess around an axis that is orthogonal to the Larmor vector because it's perfectly parallel. So you preserve spin effectively. So using this theory and some G-factor anisotropies, we were able to explain the spin-photon coupling as a function of the in-plane orientation, and we find a very good agreement with the experiment. So you have here the data points from the experiment of the spin-photon coupling as a function of the in-plane magnetic field. We find the maximum a bit displaced away from the nanowire axis due to disorder, and we have a minimum very close to 90 degrees as expected from RASHBA. We also find that the ratio between spin photon coupling and the decoherence in the system is very well explained by considering charge noise as the dominating source of decoherence. So we find a cooperativity of 1600, which is much better than what had been done with electrons. And I wanted also to mention, I don't have time to explain it in detail, but an interesting limit. In electrons, all the spin-photon coupling comes from the double dot, and once you go to a far detuned regime, so you take your detuning and you go far away to the single dot regime, In this case, you have no dipole from the double quantum dot, and in principle, you should expect, as the black curve says, that your spin-photon coupling decays very fast. This is what will happen with electrons, but with holes, even in the single dot limit, you have spin-orbit coupling. And in this case, what we find is that even in the single dot regime, you can find a finite spin-photon coupling that in principle in the future could allow to make these experiments in a more compact way. Instead of going with a double dot, you just go a single dot and do this kind of experiments in this very simplified architecture. And this had been predicted quite recently by us due to GTMR and RASHBA in Basel. So the take-home message of this part is that, I think these nanowire devices with holes are very interesting for these spin-photon experiments. You can find very large values of the spin-photon coupling, which are much better than with electrons. So in principle, we are much closer to a two-qubit gate with holes mediated by photons than in electrons. And just to conclude the talk, I hope I have shown you that the holes are interesting creatures with very cool physics, and there are things that are still to be understood, like these new mechanisms for manipulation, the one I presented today about inhomogeneous electric fields. Still, due to the spin-orbit coupling, you may think that they are not very coherent, but you can work at sweet spots where the coherence times are very good, comparable to electrons, and they provide a way to couple naturally with photons, which it's a simple way to have long-distance two-qubit gates. And finally, we have this work on single-dot spin-photon architectures as a possible future experiment in the end. So, well, with that, I thank you for your attention, and I welcome questions.